All right. Good morning, Chazelle, CK, Francis, and Denmark. Today we will discuss part of module number 10. This is the second to the last module, which contains some, what do you call this? Which contains some miscellaneous ideas about quadrature rules. Last time we talked about developing quadrature rules such as the Newton codes and the Gaussian quadrature rules. Ngayon, titingnan natin ano yung mga issues that can affect the implementation of this quadrature rules and what are ways on how to get around them or how to improve possibly the convergence or the machine implementation of these methods. All right. Since we were not able to meet last Tuesday due to the holiday, and I would like to keep the pace nung dalawang section na sabay or maging synchronized sila. I hope you will find some time to watch the recording of our class yesterday. Or if not, I hope you were able to join us live yesterday. Pero kung hindi, you can watch the recording. Nandun na siya nasa Canvas na yung link. Hanapin niyo yung discussion about Romberg integration. I think that's meeting 21. All right. Now, the nice thing about that is yung i-discuss natin ngayon, yung second part ng module number 10 is independent what from the content of the discussion yesterday. So pwedeng you stay with me today even if you haven't watched the recording yet kasi independent nga naman sila. All right? So just some housekeeping matters first. You will have lab exercise 6 on Monday, December 6th. Your lab instructors will be more than happy to assist you. And specifically for the exercise this week, it's a little. I actually like the exercise this week kasi hindi siya straightforward na application nung Romberg integration at saka nitong pag-uusapan natin today, which is about numerical integration anomalies. Right? Maganda siya. Pero meron mga steps kayong dadaanan bago nyo ma-apply yung Romberg integration saka yung synthesis between the Romberg integration and integration anomalies. So I hope you can join your lab instructors on Monday because they will guide you, especially medyo yun nga, maraming intermediate steps yung exercise for this week. All right? So the deadline for the exercise is anyway right before midnight on Monday. So if you will be able to do the lab exercise during your class on Monday, that will be good. No rush. Meron pa kayong hanggang midnight on Monday to finish it. Okay. And then I will be on leave starting tomorrow until Wednesday morning. So that means I won't be able to join you live on Tuesday. So what I'll do is either I'll prepare a recording and I'll upload it probably Tuesday night or early Wednesday para dun sa susunod na module, the start of module 11. Itatry ko siyang gawin tonight pero mukhang hindi ko na siya kakayanin. So probably by Tuesday night ko na lang i-upload yung recording for the first part of module 11. Tapos para pagbalik natin, pag-meet natin Thursday next week, will be on the second half of module 11. But let me see the schedule. Pwede kasing hindi tayo magklase ng 7, 2 meetings for module 11. So we can do that. Kaya lang cutting close na pala kasi after this coming Monday, dalawang Mondays na lang yung natitira. We only have December 6, 13, and 20. So December 6, Exer 6. Tapos sa 20, hopefully nandun yung problem set. Okay? So no choice pala talaga ako pero dapat mag-recording ako para sa module 11. So yun na lang. I expect the recording for the first part of module 11 sometime around Tuesday evening. All right? Para mapanood nyo siya. Sige, gawin ko na lang by probably, yeah, I'll try Tuesday evening, if not Wednesday afternoon. So, para ready kayo for our discussion on Thursday. All right? So, para second half na ng module 11, parang schedule natin ganito yung itsura. Exercise 6 on December 6, XOR 7 on December 13, and then you will have the problem set probably I'll give it December 14. Tas ang deadline niya ay December 20. So I hope that is fine with you guys. Yun ay assuming matatapos natin yung buong coverage ng course by December 9. Okay? Is that good, guys? And then yung project ay siguro ibibigay ko yung detalye next week. I'll think about it over my vacation leave ngayong weekend. But you can start talking among yourselves kung may gusto kayo, kung may preferred kayo na ka-group. Yung ka-group nyo for the final project need not be part of your lab. So pwede kayo mag-grouping. Hindi ko pa lang naiisip kung ilan yung maximum members per group. How many do you think? Of course, pwede naman mag-isa. Kung mas comfortable kayong mag-work mag-isa, it's also fine with me. But it will be great if you can work in groups para distributed yung work. Siguro maggagawa na lang ako ng Google Sheet para doon maglagay lahat ng mga wala pang ka-group para in case you are willing to work in a group and then you don't if you don't know anyone in the class or you don't have any preference, I can make the grouping for you. Pero kung meron na kayong gusto mga ka-group, then that's also fine with me. I'll just include in the guidelines that I will release next week kung ilan yung maximum members per group. Right? At kung saan kayo magsasubmit ng pangalan kung gusto nyo ako yung maghanap ng mga ka-group para sa inyo. Right? So the recording yesterday discussed Romberg integration, so that will take care of objective number 1. Now we will look at objective number 2, which is on the identification and solving of numerical integration anomalies. When I say numerical integration anomalies, ito yung mga problema dun sa integrand kung bakit magfe-fail o mag-underperform yung mga numerical integration routines na na-discuss natin. Kasi last time, we presented a wide variety of quadrature rules. Una nga, yung Newton codes, which has its own beauty. Kasi una, mag-work siya sa kahit anong exabytes na given. Kasi ang idea, nagkagawa lang naman tayo ng interpolating polynomial and we replace the integrand by the interpolating polynomial and we'll get a nice approximate. Kung gusto mong mas maganda yung or mas maganda yung approximation, you can use a composite rule by introducing more points, but on each of the subintervals induced by these points, gagawa tayo ng isang lower order quadrature technique para hindi siya maging subject sa Runge phenomenon. Okay? Pangalawa yung Gaussian or Gauss-Legendre quadrature rules, which specifically choose the exabytes to gain the maximum degree of precision. Okay? So, marami tayong choices. Pero, kahit na meron tayong mga choices na ito, minsan wala tayong magawa pero mag-succumb sa numerical artifacts na nakukuha mula sa machine implementation nito mga quadrature formulas na ito. And we will look at bakit nangyayari to and specifically what's the problem with the integrands that causes these problems and how to remedy them. Okay, and usually the remedies will just be a simple substitution or a simple trick that we can use on the integrand. Okay, now a more detailed discussion of these examples can be found in this book by Brady. So you can take a look at it, A Friendly Introduction to Numerical Analysis. I actually like this book. Naghahanap nga ako ng hard copy pero wala pa rin ako nakikita. Pero this is a good one, especially for undergraduate numerical analysis. So let me go to that section. Okay, integration anomalies. Okay, so we'll check first. Tingnan natin. To illustrate ano yung ibig sabihin, ano yung gusto kong sabihin with anomalies, ito yung, tingnan natin tong example na to, kung saan makikita natin yung underperformance ng numerical integration formulas natin. So let's consider the integral of x to the 2/3 from 0 to 1. Now, this is easy to calculate kasi yung integral, isang antiderivative ni x to the 2/3 ay 3/5 x to the 5/3. So actually, this can be easily done by hand. Pero kung i-input mo siya sa isang computer, alright? So kasi nga, ang idea natin, kaya ko siyang i-integrate by hand. So ibig sabihin, dapat hindi mahirapan yung computer pag pinagamit ko sa kanya yung numerical integration formulas, alright? So let's see. Pag pinagawa ko to sa computer using the quadrature formulas, namely trapezoidal rule, Simpson's rule, the midpoint rule, and the two-point Gaussian, all right? Ibig sabihin, ito ay composite rules yung ginagamit ko. So, halimbawa, meron akong 2 points. Ito yung makukuha akong trapezoidal, Simpson's, midpoint, and two-point Gaussian. Okay? Pag n equals 4 na, gumamit ako ng trapezoidal rule. Ito yung error. Okay? So, yung error bumaba na sa 1.2 times 10 to the negative 2. Pag gumamit ako ng composite Simpson's rule, ito yung makukuha kong error, which is good, 4.2 times 10 to the minus 3. I mean good kasi knowing na apat lang yung points na ginamit natin. Ito naman yung para sa midpoint rule. Tapos para sa composite two-point Gaussian, so ibig sabihin meron akong apat na points supposedly na gagamitin, no? So ibig sabihin magagawa ko ng composite Gaussian rule doon sa dalawang subintervals, or actually ilang subintervals? Sa tatlong subintervals induced by the 4 points. Okay? So yun yung ibig sabihin ko dito ng two-point Gaussian. Alright? Now, we can repeat the experiments using more points. So if we'll use 8 points, ito yung respective errors, and all the way up to 64. And everything seems good. Kaya lang, pag tinignan natin yung experimental order of convergence compared to dun sa theoretical order of convergence, for instance, the trapezoidal rule is of order big O of h squared. So ibig sabihin ang theoretical order of convergence niya ay 2. Alright? Pero pag tinignan natin yung experimental order of convergence, so titingnan ko ito divided by a power of the next thing, all right? Or actually hindi pala. This would be this guy divided by a power of 4. I will get this guy if the power is approximately 1.5986, all right? So yun yung ibig sabihin ng experimental order of convergence. So, or if you forgot, go back to your AMAS 152 notes. Nandun yung order of convergence. Or if not, you can take a look at the work text. I have a discussion there of the order of convergence and how to get the experimental order of convergence. All right. Pero looking at this data, all right, sa implementation ng method, ang order of convergence ng numerical approximates, I think I used Excel for this one, ay 1.5986 lang. So ibig sabihin, yung error is a big O of h to the 1.5986, meaning the error vanishes as fast as how h to the 1.5986 approaches 0. Pero ang ini-expect natin yung trapezoidal rule, dapat ang order of convergence niya ay 2. So ibig sabihin, nag-underperform yung machine implementation natin ng trapezoidal rule compared dun sa theoretical order of convergence, right? Similarly for Simpson's rule, and we have here a bigger discrepancy because the theoretical order of convergence is 4, so meaning we expect the error to go down to 0 as fast as how h to the 4th goes to 0. However, using the experimental data that we have here, it seems that ang order of convergence lang nating nakuha ay big O of h to the 1.6651. So kasing bilis lang siya ni h to the 1.6651 pupunta kay 0 instead of the same speed as h to the 4th. The same thing happens for the midpoint and the two-point Gaussian formulas. Okay? So napakalaki ng discrepancy with the theoretical order of convergence, and that is even glaring by knowing that yung integral na ini-evaluate lang natin ay napakasimple. It's x to the 2/3. So parang wala namang problema kay x to the 2/3. Alright? Okay. So bakit nagkaganon? Ano yung naging problema with this integral? kaya hindi natin attain yung theoretical order of convergence? Well, there's a small caveat in in the quadrature rules that we have developed. Dapat ay sufficiently smooth yung mga derivatives niya. Alright? So, ibig sabihin, dapat continuous yung maraming derivatives ng functions. But our integrand here is x to the 2/3. Ano yung first derivative ng x to the 2/3? Ang derivative niya would be 2/3 x to the negative 1/3. Or you can write it as 2 over 3 cube root of x. Now, this function is not continuous over the interval 0, 1 because it is undefined at the lower bound 0. So, ibig sabihin pala, okay, although continuous yung function, wala tayong problema pag in-evaluate natin siya by hand, pero yung mga quadrature formulas ay na-derive natin para sa mga sufficiently smooth integrals over the integration, sufficiently smooth integrands over the integration interval. All right. However, x to the 2/3 is not smooth kasi yung derivative niya is not sufficiently smooth kasi yung derivative niya, yung first derivative niya ay 2 over 3 cube root of x which is not continuous on the closed interval 0, 1. Pero yung error bound para sa trapezoidal rule, Simpson's rule, midpoint rule at two-point Gaussian requires the derivatives to be continuous. All right? So may point of discontinuity yung first derivative. Walang problema pag merong point of discontinuity yung derivative pag integration by hand. Pero pag quadrature rule yung ginamit, magkakaroon tayo ng problema kasi yung error ay nakadepende doon sa derivatives nung integrand. Okay? So that's a problem here. Tapos sitingnan natin, paano natin ito ma-address? All right? How can we make this function smooth? All right. And we will do some clever substitutions to do that. Okay. Now, and that gives us the first anomaly. Pag meron tayong fractional exponents. Pag meron ka kasing fractional exponents, nagiging hindi differentiable yung function. Actually, kailangan ba ay yeah. Usually nagiging problema siya sa fractional exponents kasi pag fractional exponents, posibleng yung denominator ay magkaroon ng radical. Tapos yung radical, especially if the index is even, nagiging hindi siya differentiable sa zero. Alright? Actually, basta pala nagkaroon ng x sa denominator, hindi na siya magiging differentiable sa zero, no? Pero if your exponents are fractional, madaling solusyonan yung discontinuity of the first derivative at one of the endpoints. All right? Because now what we can do is to just remove the fractional exponent. Okay? Now, if this is our function, for instance, nawala yung dx, all right? So, pwede kong gawin ay, what would be the proper substitution so that the exponent will not be fractional anymore? All right. So what we can do here is to let x be equal to u cubed. Kasi nga gusto ko mawala yung fractional exponent. So here, I can let x be equal to u cubed so that x to the 2/3 becomes what? Becomes u. So kailangan ko lang siyang bakit mali yung sagot ko? 3u to the 4th. If I will let x to be equal to u cubed, tama pala. So this will, yeah. All right. Naewan ako sa, sa substitution. All right. But if x is equal to u cubed, so that means x to the 2/3 will be, tama ba? Ito ay magiging u. Erase ko sa 2/3, erase ko sa 2/3, u squared. All right, there we go. I think that's right. So x to the 2/3 will be equal to u squared. And then dahil nagpalit ako ng variable, dapat magpapalit din ako ng differential. So the dx should be replaced by du, but implicit differentiation will tell us that dx is equal to 3u squared du. All right. Now, putting these substitutions into our integral a, we can write it as x to the 2/3 will be replaced by u squared. Dx will be replaced by 3u squared du. All right. And then now we need also to change the bounds. When x is 0, all right, u will be equal to 0 pa rin. So this will be a 0. Okay. And then if x is equal to 1, so magiging 1 to, si u dapat equal din kay 1. All right. So I will retain the bounds. So now I can integrate 3u to the fourth du from 0 to 1 instead of x to the 2/3 from 0 to 1, because they will just give the same integrals, or the same value for the definite integral. Okay. And this is better because this guy is just a polynomial, and polynomials are smoothed everywhere. So this will be smoothed over the interval 0 to 1. So nawala na yung anomaly caused by a fractional exponent, in particular, the first derivative of the original integrand being discontinuous, all right, at the lower bound 0. And then true enough, if I will replace this integral a by an equivalent integral here, the only difference is, again, the integrand here is a polynomial, but they will give me the same constant value for a. Pag ginamit ko yung mga quadrature rules again, na ginamit natin kanina para kay x to the 2/3, ginamit ko siya kay 3u to the 4th, magigain na natin yung theoretical order of convergence. All right? You see that the promise for the trapezoidal rule is that it would be a big O of h squared. And true enough, the machine implementation gave us a sequence of approximates that converges as fast as how h to the 1.9939 approaches 0. At kung makikita nyo, ganun din yung nangyari para sa Simpson's midpoint at two-point Gaussian. So I hope here you appreciate that the minor change, the seemingly minor change in the variable, parang gave us back yung discrepancy between the theoretical order of convergence and the experimental order of convergence. Hindi na pala natin kailangan mag-develop ng bagong technique. Kailangan lang nating isulat yung integral in a nicer way, in a clever way. All right? Tapos paano natin yung nagawa? Tinrack down natin ano yung naging problema. And we found out na yung first derivative ng function f o ng integrand f ay discontinuous dun sa lower bound. So if you will just be thinking from a pure math point of view, wala namang problema yon. Kasi ang kailangan ko lang ay continuity ng integrand para mag-exist yung integral. Alright? Pero since we are implementing it in a machine, kailangan nating tingnan ano ba yung mga nadagdag na requirements para dun sa quadrature rules. Sa quadrature rules, dapat sufficiently smooth yung integrand. Pero yung x to the 2/3, hindi siya ganun ka-smooth kasi yung first derivative niya ay hindi continuous. And that actually cost us a large discrepancy between the experimental order of convergence and the theoretical order of convergence. Luckily, we had a clever way of how to work with fractional exponents. Pag fractional yung exponents, do the proper substitution para mawala yung pagiging fraction niya. Pag hindi na fractional yung exponents, magiging polynomial na lang yung integrand. Okay? So I hope you can discern the pattern from there. Ito yung general technique kapag fractional yung exponents. All right? So for the next examples, I will just discuss several cases. Tapos ano yung appropriate substitutions para sa kanila. Hindi ko na ipapakita yung table para sa kanila, but believe me, those substitutions actually will improve the experimental order of convergence and make it closer and closer to the theoretical order of convergence. Okay? Now, isa pang problema na posible nating makita ay sa mga removable discontinuity. And actually, removable discontinuities would be a problem even from the theoretical standpoint. Kasi ang requirement para maging integrable ang isang function sa closed interval, dapat yung function ay continuous sa closed interval. All right? However, if you look at the integrand in example 10.3, ito yung integrand, e to the power x minus 1 all over x. And when x is equal to 0, pag nag-0 yan, discontinuous na yung function kasi yung function ay hindi defined when f of x is equal to 0. Actually, removable discontinuities are easy to deal with kasi sa integration theory, pag nagbago yung isang point, yung value sa isang point, hindi malaki yung epekto niya sa integral. Alright? So the only problem here is at f of 0. Alright? Because f of 0 is not defined. But luckily, it's a removable discontinuity. Hopefully, natatandaan nyo kailan nga ba removable discontinuity. Removable discontinuity siya kapag ka nag-exist yung limit, pero hindi siya equal dun sa function value. In our case, that is true because the limit do exist. You just need to apply L'Hopital's rule to the integrand. Pero yung f of 0 ay undefined. Obviously, kasi magze-zero yung denominator. Okay? So the thing here is, magkakaroon lang pala ako ng problema rito ay kapag ka si x equals 0 ay naging isa sa mga abscissas. Alright? But before I go there, tingnan ko kung magkakaroon pa ako ng mas malaking problema aside from the removable discontinuity. Alright? Actually, paano natin makikita na removable or paano natin ma-verify na indeed yun lang yung naging problema nung integrand na yun? Let's look at the Taylor series expansion of the integrand. Okay? So, -1, kinopya ko lang siya. Ayun siya yung first term doon. Tapos, kinuha ko yung Taylor series expansion ni e to the power x. Ito yung makukuha kong series expansion niya. Alright? Now, and then over x, kinopya ko lang yan mula dun sa given. Something wrong. All right, hopefully I'm back. Do you guys hear me now? Nag-notify kasi sa akin na naputol daw ako for a moment there. So hopefully I'm back. I was saying that here I'm getting the Taylor series expansion or the Maclaurin series expansion of the integrand. So ito lang siya, right? If I simplify this, -1 plus 1 will be canceled. I'll be left with this, guys. Divided by x, I will get this one. And this is actually just an infinite series of polynomial terms. So ibig sabihin, ito ay infinitely smooth na kasi when x is not equal to 0, this is just an extended polynomial. So really, the only problem here is the removable discontinuity at x equals 0, which will cause us some trouble if x equals 0 is one of the integration abscissas. Okay. So ang remedy pag removable discontinuity naman yung integrand, edi iset mo lang yung function value dun sa point of removable discontinuity to be the limit. Okay. Again, the function is undefined at x equals 0, but the limit exists. So to remove the removable discontinuity, let the limit be equal to the function value at the original point of discontinuity. All right? So ito yung application ng pinapagawa sa inyo ng Math 36 na redefine the function to make it continuous. Kasi mahalaga siya para sa integration. So if you are using a quadrature formula that will require x equals 0 to be an abscissa, you can just say, okay, I'll just assign 1 to its function value. Because this guy now is a continuous function on the integration interval -1 to 1, all right? And we only change the function value at one point. And changing the function value at a finite number of points doesn't matter sa integration. So sa mga nagmamat 155 dyan, makikita nyo later, hopefully maabot natin na pag nagpalit ako ng function value sa isang set of measures 0, hindi nagbabago yung value ng integral. Alright? So yun din yung idea dito. Kaya pwede tayong magpalit ng function value sa isang point, or actually sa finite number of points, and that will not spell too much trouble for our approximate for the integral. Because theoretically, wala dapat mababago, pero since quadrature points sila, posibleng may pagbabago dun sa approximation, but that shouldn't be very very major, especially if the function value that you chose is the limit of the integrand as x approaches the number of discontinuity or the point of discontinuity. Okay? So summary here, pag removable discontinuity, yung cause ng underperformance, i-remove nyo lang yung discontinuity. The usual way you do it in Math 36. Okay? Okay, so we can also look at integrals with combo anomalies. Ibig sabihin, one anomaly on top of the other. So let's see example 4. Here we have the b equals the integral of sine x over the square root of x dx from 0 to 1. The glaring anomaly here is that the function is discontinuous at x equals 0. All right. So x equals 0, magiging discontinuous siya dyan. Okay. So tandaan natin, yun yung isang problema. Okay. Next question is this sufficiently smooth? All right. So yun yung pa yung isa nating kailang i-resolve. All right. So tingnan muna natin yung kung yung discontinuity ba ay removable. Okay. So this is our function f. Undefined siya obviously kay 0. But if we take the limit of f as x approaches 0, the limit exists and actually it is equal to 0. So if that is the only problem, then we could just have simply redefined the integrand, assigning the value 0 at x equals 0. Pero medyo may hinala pa ako rito na posibleng magkaroon ng problema kasi meron akong x to the 1/2 dun sa denominator. So that means I have fractional exponents. Okay? Which should remind you of our first example. Now, true enough, if you'll try to analyze the integrand further, you look at the Taylor series expansion or the Maclaurin series expansion of sine x. You get this guy in the numerator. And then I'll have x to the 1/2 in the denominator. Okay. If I simplify things, we'll get this, the extended series, but these are summations of powers of x's where the powers are fractional. And remember, what we learned from the first example is that fractional exponents spell some troubles for our quadrature rules. So, pwede kong tingnan, ito na lang yung integrand. Actually, two birds in one stone. Yung mangyayari kapag ka yung integrand, pinalitan ko lamang neto. Okay? So, nawawala yung discontinuity because this guy is continuous at x equals 0. Ang problema nga lamang ay meron siyang fractional exponent which will make it not sufficiently smooth. Right? So pwede kong gawin, itry kong tanggalin yung fractional exponents. So kung ito yung simplified form ni x, alright? So makikita natin na yung mga powers ay may denominator na 2. Alright? So dahil may denominator na 2 yung mga powers, pwedeng gawin ko ay, kasi gusto ko mawala yung fraction. So I will let x to be equal to u squared. Right? Because if I do so, when x is replaced by u squared, lahat ng mga powers na to ay magkakaroon ng exponents na integer na lang. Okay? But again, this will require the change in the differential. So this will require dx to be replaced by 2u du. But that's fine because 2u is a polynomial. So I don't think that will cause us too much trouble. So either you do the substitution here. Kaya lang magkakaproblema pala tayo doon kasi infinite series to. Kailangan yung putulin yung infinite series up to some points or up to some point kung ilang terms yung gusto nyong i-keep dun sa summation. So that should be fine. All right. And then, or another option is to do the substitution here. Maybe we can solve both our problems, yung removable discontinuity at saka yung fractional exponents in one go. And true enough, if I will use this substitution in the original integral, we will get b equals this. Ang b ay equal lang sa integral ng 2 sine u squared from 0 to 1. Okay? And what can we say about this guy? Oh, this is just a sine function, all right? A multiple of the sine function. Essentially composition with x squared. So 2 sine u squared. Si u squared ay continuous. Si sine ay continuous. So yung composition nila ay continuous. And actually not just that. U squared is infinitely differentiable. Sine is infinitely differentiable. So their composition will be infinitely differentiable. So ibig sabihin, ito ay infinitely differentiable. So that means it is infinitely smooth. So ibig sabihin, wala tayong magiging problema when we apply the numerical integration formulas to this integral instead of the original one. Kasi ito, magkakaroon tayo ng underperformance. Ito, guaranteed na mawawala yung underperformance. So nakita nyo, kahit na kaya kong i-remove yung discontinuity, kailangan ko pang i-check. Like the one in example 3, isa lang talaga yung problema natin, removable discontinuity. Pero sa example 4, aside from the removable discontinuity, nagkaroon pa tayo ng problema with fractional exponents. But luckily, a single substitution will solve both of those problems. Okay? And sure enough, I think nilaro ko rin itong example na to. Pag gumamit ako ng adaptive or composite 3-point Gaussian quadrature rule, kailangan ko lamang ng 87 function evaluations para yung approximate ko ay accurate up to 5 times 10 to the negative 11. So, pero kung gagawin ko yung parehas na method, yung adaptive 3-point Gaussian quadrature rule, para yung error ay hindi lumampas ng 5 times 10 to the negative 11, it will take me 677 function evaluations to do that. Okay, so medyo ang laki nung improvement. From 677 required, bumaba siya sa 87, and yet I get the same quality of the results as far as accuracy is concerned. Okay, so nakita niyo yung maliit na change dun sa variable, save us some computation time or computation resources. All right. So any questions so far? Okay, kung wala naman, tingnan natin yung mas komplikado na example. So sa example 5, ang anomaly naman dito ay essential discontinuity. So kaya nating solusyonan yung ilang klase ng mga essential discontinuity. Actually, we will consider two. We'll look at two cases of essential discontinuities na pwede nating solusyonan. The first one is called the algebraic case. Okay, wherein the function has an essential discontinuity. Usually that means the limit doesn't exist or the limit is plus or minus infinity. So pagka sinabi nating algebraic discontinuity, the function tends to behave like x minus a to the power negative alpha, where alpha is a positive number. Okay. The second one is logarithmic discontinuity, where the function behaves like ln of x minus a. All right. Especially for numbers near a. Kasi pagka malapit yung number kay a, x minus a will be close to 0. ln of something close to 0 will be a very large number. Kasi ang limit ng ln as x approaches 0 ay negative infinity. Ganun din dito, kasi kapag si x ay malapit kay a, ito ay magzi-0. 0 raised to a negative exponent will give us a very large number. Actually, 0 raised to a negative exponent is undefined, pero pag ganun yung form ng limit, positive or negative infinity yung makukuha niyong sagot. Okay? So, yun yung mga essential discontinuities na kaya nating solusyonan. So, let's see this monster integrand in example 5. Napaka-komplikado ng function, and from afar, even at just looking at the integrand, you will smell some trouble. Alam mo na kagad na magkakaroon dyan at magkakaroon ng problema. The first problem is, okay, the function is discontinuous at x equals 0, kasi obviously the function value will not exist at x equals 0. But even more than that, pag kinuha natin yung limit ng integrand, as x approaches 0, makukuha natin ay negative infinity, right? Or at least as x approaches 0 coming from the right. So ibig sabihin, hindi natin magagawa yung technique natin kanina na tanggalin lamang yung discontinuity, because here the discontinuity is essential. All right? So kasi yung limit ng f ay hindi nag-exist, kasi yung limit ni f as x approaches 0 from the right ay negative infinity. Now let's analyze what could be done for this integrand. So kukunin ko lang yung Taylor series expansion. Okay? So tingnan natin kung paano kinuha yung Taylor series expansion. Well, I'll start with this guy. This is x to the 2/3 in the denominator. So I can write it as x to the minus 2/3, as a factor, okay? And then yung cosine ng root ng fifth root ng x minus 1 has this Maclaurin has this Taylor series expansion, okay? Ito yung expansion niya. And then yung e to the root x, ito yung expansion niya. Tapos yung 1 over 1 plus cube root of x, ito naman yung expansion niya. Okay? So kinuha ko lang yung expansion ng lahat ng mga terms para madali ko siyang i-manipulate. Okay? And then you can multiply the first few terms of this guys and you will get this. And what we observe here is that there is a negative exponent here, all right? Pero fractional yung datingan ng mga exponents, all right? So and we know that fractional exponents will cause us some troubles, okay? So ano yung makikita ko rito? Ano yung pattern? May pattern ba rito? Okay, it seems that all the exponents can be written as a fraction with 30 as the denominator. Actually, makikita natin siya dito, dun sa original problem. Kasi yung exponents dito ay 1/5, exponent ay 1/2, exponent ay 2/3, exponent ay 1/3. The least common denominator between these fractions is 30, right? Tama nga ba? 30 na yung list. Si 15 ay hindi, si 10 ay hindi. So 30 na nga yung least common denominator para dun sa mga exponents. So to remove the fractional exponents that we see here in the Taylor series expansion, so we will let x be equal to u to the 30th. And when we do that, when we replace x by u to the 30th, we'll get this integrand. Okay. And then here, will we have any problems here? Okay, the denominator will not be equal to 0 because we have a 1 plus u to the 10. So the denominator won't be 0. So this is well defined from 0 to 1. And then all components here are continuous. So ibig sabihin, actually not just continuous, but all of them are smooth. So ibig sabihin, smooth na yung integrand. So we don't expect any more problem with this integral. Okay. Hold on, guys. All right. Medyo kinailangan kong kunin yung Taylor series expansion kasi para malaman ko na yung fractional exponents lang yung nagiging problema. And I can only know that if I can express the functions as series of powers of x. Okay, kaya kinailangan kong isulat yung Taylor series expansion nila. Okay. So kung nagmo-model kayo or may research kayo tapos ito yung integrand, ni-run nyo yung trapezoidal rule o kung anumang rule yung ginagamit nyo para sa numerical integration, tapos ang bagal niya mag-converge or mali yung binibigay niyang sagot or malayo dun sa actual answer o dun sa answer na ina-expect nyo. So pwede nyo gawin tong substitution na to, alright? And that will give you a smoother integrand, which hopefully will work better for your quadrature formulas. Okay? Now, that's for algebraic essential discontinuities. Para naman sa logarithmic essential discontinuity, actually, I don't think this is a good template. Parang mag-work lang siya for specific logarithmic essential discontinuities kasi kailangan nating tanggalin or i-separate kung ano yung nagko-cause nung problema. So ganun yung usual technique. Walang one size fit all dito sa pagtatanggal ng mga integration anomalies. So you need to be a little bit creative about this kasi nga baka yung method na suggested, for example 6, will not work for other functions with logarithmic essential discontinuity, right? So but let's see nevertheless ano yung pwede natin gawin. Let's consider the integral of ln x over 1 plus x squared from 0 to 1, okay? Now, if we let the, of course, Okay, the function is not defined when x is equal to 0 kasi yung ln of 0 is undefined. So the function we know is obviously discontinuous at x equals 0. But what type of discontinuity? If we take the limit of f as x approaches 0 coming from the right, we will get negative infinity. All right? Dahil negative infinity yan, meron siyang essential discontinuity. And further, the discontinuity is in the form of a logarithm or logarithmic nga yung essential discontinuity. Not just because ln yung involved dito, pero if I take the Taylor series expansion of our integrand, so yung ln x, copying ko lang siya. Okay? Yung Taylor series expansion ng 1 over 1 plus x squared ay ito. All right? So f can be looked at as the series that looks like this. Okay? Tapos, ano ba yung nangyayari sa bawat isang term? Right? Na may power na x. Right? So whenever you have a power of x, a positive power of x, yung limit ng x to the alpha times ln x. All right? So tinitingnan ko yung behavior nito, which has alpha equals 2. Ito, where alpha is equal to x to the, is equal to 4. Dito ang alpha ko ay equal kay 6. Pero the idea is, whenever alpha is a positive number, the limit of x to the alpha times ln x ay equal kay 0. Okay? So you can use tricks that you learned in math 36 to evaluate the limit, pero madali lang siyang i-analyze crudely kasi yung x to the power a grows faster than ln x or moves faster than ln x. So what drives the day in this limit is the factor x to the alpha. But x to the alpha approaches 0 when x approaches 0, so this guy will approach 0 as well. So ibig sabihin pala, as x approaches 0, this guy goes to 0, this guy goes to 0, this guy goes to 0, and everything else after. And natitira lang talaga yung ln x. But as x approaches 0, ln x approaches negative infinity. Kaya may natira na limit doon ay negative infinity. But what we see here is, yeah, it seems that the problem lies on this guy, the ln term. So yun yung nagko-cause ng essential discontinuity. Okay? Now, what we can do instead is to split the integral into two pieces. In particular here, I split the integral into these two guys. Okay? Pero yung linearity ng integral ay sasabihin lang na ito ay equal sa integral from 0 to 1 ng ln x 1 plus x squared minus ln x plus ln x dx, right? Which simplifies back to the original integrand. Pero ang kagandahan nito ay, itong unang term ay itong expansion na to minus ln x, alright? Kaya ako nag-minus ng ln x. So, ibig sabihin, mawawala lang tong first term, matitira ito. Tapos yung limit nito as x approaches 0 ay magiging equal lang kay 0. So, yung discontinuity nung first integrand, nung unang integrand, namely ln x over 1 plus x squared minus ln x, ay removable na lamang sa x equals 0. Kasi nga ang series expansion nitong bagong integrand na to ay negative x squared ln x plus x to the fourth ln x minus x to the sixth ln x and so on. So nawala na yung nagpa-infinite dun sa limit niya. So dito, pwede kong gawin na lamang yung technique na natutunan natin before on how to deal with those with removable discontinuities. Okay? And then, etong ln x dx, pwede mo siyang ipa-compute numerically, pero kailangan mo mag-adjust ng kaunti kasi ito ay hindi rin to smooth kapag when x is near 0. But you can solve for this manually using integration by parts and improper integrals that you learned from Math 36. So it is suggested that this be evaluated by hand. It is not that difficult. And then evaluate this using your quadrature formulas. Okay? Kasi removable na lang yung discontinuity sa x equals 0 dito. Okay? So yeah, Ay, yun yung para paano ma-combat yung mga discontinuities. There are other forms of discontinuity other than exponential and logarithmic. So, ito lang yung dalawang cases na pinersend ko. Alright? So, don't worry though, dahil hindi naman tayo nag-dwell dito ng masyado, hindi ako magbibigay ng problem that is beyond the form given in the examples here. So kayo mag-worry na kailangan nyo sauluhin lahat ng Taylor series expansion and so on. So gusto ko lang ma-appreciate nyo ano yung mga pwedeng gamitin. Kasi when I was teaching this, before I left for my PhD, parang napaka-superficial naman ito. Saan ko to gagamitin? Alright? Pero when I took a course in electrical engineering during my PhD studies. Tapos kailangan namin mag-evaluate ng mga integrals. So dun sa pag-i-integrate, nagkaroon doon ng mga essential discontinuity o ang tawag doon ay mga singularities. Now, hindi nag-work yung numerical techniques, yung quadrature rules na supposedly gagamitin namin para isulat yung program. Pero there was a nice way, something that engineers usually use, at least electrical engineers. Meron silang mga method na paano ma-separate yung singularity o yung nagkakos ng essential discontinuity. May tinatawag silang Nystrom method and so on. Pero the idea is something similar to this, an elevated version of this na iniwalay niya lang yung discontinuity. Nag-introduce siya ng minus ln x para ito ay magkaroon na lamang ng removable discontinuity. Tapos yung ln(x) can be integrated using techniques you learned when you talk about improper integrals in Math 36. So siguro ngayon di nyo pa makita yung utility ng mga methods na to, pero yeah, they really, I can vouch for it. They really appear in applications. Okay. So I would just like to finish the module. There are still, I think, 2 examples left, and I'll just borrow the next 8 minutes to discuss them. Itong last set of examples would be less difficult than essential discontinuity because the problem now here ay improper yung integral, not because of a discontinuity, but because of an infinite bound. Kapag ka naman infinite yung bound, all right, kailangan lang nating pumili ng appropriate substitution para maging finite yung bounds. Tapos pag naging finite na yung bounds, kailangan nating tingnan ano pa yung mga ibang posibleng issues katulad ng mga na-discuss na natin kanina. Alright? For instance, example 7, ito yung ating integral. Obviously, it is improper even though the function is continuous on the integration interval, pero yung upper limit ay positive infinity. Okay? So you just need to think of a way on how to remove the infinite bound in here. All right. A usual trick is to let x be equal to 1 over u. Kasi kapag si x ay equal kay 1 over u, when x is equal to 1, so ibig sabihin magkakaroon tayo ng 1 over u, that means u is equal to 1. Okay? So yun yung lower limit dun sa bago kong integral after the substitution. Okay? Tapos when when x is positive infinity, all right? So magkakaroon ng positive infinity over 1 over u. Nilagyan ko siya ng quotation marks kasi baka magalit yung mga pure mathematicians na anong ibig sabihin ng pinagsusulat mo dyan, right? So ano lang natin to, pang-analyze lang. So kailan nagiging positive infinity ang 1 over u? That happens when u is equal to 0, right? Or something close to 0 will give us a very large quotient. So the upper limit here will just be equal to 0. And then if you let x be equal to 1 over u, then dx will be negative 1 over u squared. So that's how we got that. X is replaced by 1 over u, x was replaced by 1 over u, and then we'll get this integral. Okay. Although this integral has finite bounds, pero nagkaroon naman tayo ng discontinuity sa x equals 0. Alright? So kasi kasama na si 0 sa integration interval, meron tayong u sa denominator, so that means this will have a discontinuity. Alright? So you need to analyze this further and see ano yung klase ng discontinuity ang meron siya and address that kind of discontinuity using the same tricks that we used before. Okay? So kaya dito kailangan nyo pa siyang i-check for other anomalies as discussed above. And I think the main problem here is when u is equal to 0. Try to remedy that using the tricks that we learned earlier. Okay? Now, meron pang mga ibang cases, mga hybrid cases, katulad ng example 8, when we have infinite bound plus discontinuity. All right. Let's see why is that so. Mhm, mhm. Ano pa yung isang point of discontinuity nito? Alam ko yung infinite bound, the positive infinity, will cause us some troubles. Pero this guy can be simplified as t squared over e to the t squared. So where is the problem? Will we have a problem when x is equal to 0, when t is equal to 0? Yeah, I don't think there's a big issue when t is equal to 0. Oh, I guess that will happen after the substitution. Okay. Kasi pwede ko uling gamitin ditong substitution ay x equals 1 over u para mawala yung infinite dun sa bound. So yung integral, magiging integral na lang from 0 to 1 as we have seen before. Pero pag ginawa natin yung substitution na yon, magkakaroon tayo ng dalawang integrals of this form. Okay? Now, dito pala sa una, hindi tayo magkakaroon ng problema. Bakit ko siya pinaghiwalay? Dahil ba sa substitution? 1 to positive infinity, 1. Okay, I see. Kasi kapag ka si xi equal kay 0, okay, 1 over u, right? Ito yung isosolve natin. Wala tayong solution. So hindi ko nga pala mapapalitan yung lower limit. Okay? Kasi when t is equal to 0, and if I will let t be equal to 1 over u, I cannot replace the lower limit. Kaya ang ginawa ko ay in-split ko pala muna yung integral to be an integral from 0 to 1, tapos plus integral from 1 to positive infinity. Kasi dito sa pangalawa, pwede kong gamitin yung same substitution trick that we used in example 7 para magkaroon ng integral of this form. Tapos itong integral na to ay wala tayong problema kasi ito ay continuous over the interval 0 to 1. Okay, hindi na to improper integral. So I don't think there are anomalies involved that will cause numerical quadrature rules to underperform for the first integral. Then kindly check ano yung mangyayari dun sa pangalawa. Okay? Yung pangalawa, may problema pa tayo dyan kasi discontinuous siya sa u equals 0. All right? So again, check for other anomalies before applying the quadrature rules for the second term here. And then let's see, example 9, infinite parehas yung bound, so same trick. Hatiin natin siya sa, actually ngayon, hatiin natin siya sa 4 na integrals. Actually, pwede mo siyang hatiin sa 4, say, negative infinity to negative 1, then negative 1 to 1, and then 1 to positive infinity. Ilan yan? 3 lang pala. Alright, tapos gamitin mo yung substitution na 1 over u na katulad ng ginawa natin sa examples 7 and 8. Pero magkakaroon ka doon ng 3 integrals. Right? Na iba-iba yung bounds at iba-iba yung itsura. Pero another approach would be to use the substitution rule, especially if both of them have plus or minus infinities. So you can let x be equal to tangent theta. All right. When x is equal to tangent theta, then magkakaroon tayo ng negative infinity equals tangent theta, right? So ano dapat yung value ni theta to get a tangent that is very close, a number that is approaching negative infinity? Remember, ito ay sine theta over cosine theta. So gusto natin yung cosine theta ay mag-approach ng 0, okay? And that will happen at negative pi over 2. Kaya yung negative infinity after the substitution became negative pi over 2. Tapos, kung positive infinity naman yan, gusto natin yung cosine ay mag-approach sa 0, pero yung quotient dapat ay positive. So that will happen when theta is equal to pi over 2. Okay. Kaya yun yung bounds. And we were able to do this, to perform the substitution, okay, without having to split the integral into 3 pieces. Okay, nagawa ko siya in one go. So ito lang yung integral, but again, before I apply numerical quadrature formulas here, I need to check meron pa bang posibleng maging problema dun sa integrand, dun sa bagong integrand ni G. All right? Specifically, there might be a discontinuity at a value theta that will cause the denominator to be equal to negative, to be equal to 0. So just kindly check that out and remedy it accordingly, base dun sa mga na-discuss natin earlier. Okay? Now, in the exercise, you will be asked to do that, all right? So, pero simple lang naman yung function, okay? Nagagamitin. Meron kang radicals exponent. So I think here you'll just need to remove the radical from the exponent by using the appropriate substitution for x. The resulting function will be continuous. Tapos ang catch nga lang dito ay kailangan gamitin yung Romberg integration or to find the minimum number of rows sa Romberg integration para yung relative computable error estimate, which was discussed in the lecture yesterday, ay hindi tataas ng 10 to the minus 4. So pwedeng gumawa kayo ng table ng Romberg integration. Tingnan nyo ilan yung kailangan tables, ilan yung rows na kailangan sa Romberg integration tableau para yung relative computable error ay maging less than 10 to the minus 4. So hindi to theoretical computation kasi hindi ko diniscuss yung error estimate para sa Romberg integration. So kailangan yung i-implement yung Romberg integration para dun sa function that will result after your appropriate substitution para mapaganda yung integrand. Okay? So pag nakuha nyo na yung mas magandang integral, gamitin nyo yung Romberg integration pero row by row. Tapos pag nakabuo na kayo ng rows, computin nyo lagi yung relative computable error estimate, take note of what the value is, tingnan nyo kung kailan siya unang naging less than 10 to the minus 4. And that will be your answer to the minimum number of rows needed in the Romberg integration tableau. All right? And then yung problem number 1, I'll let your lab instructors talk more about this kasi medyo wala na tayong time. Pwede nyo naman sundan yung instructions pero it would be fine if you will ask your lab instructors for help with this one. Okay? Kasi pag nagkamali kayo dun sa pag-construct ng data, hindi na rin maganda yung makukuha yung answer sa part B and part C. All right? So I think that's it for today. Do you guys have some questions? All right, so if none, then that concludes Module 10. So we only have one module left. That's Module 11, which would be on Monte Carlo simulations. And I have said we will not meet on Tuesday. I am on leave until Wednesday morning. So ang balik na natin live ay Thursday. Pero I would like you to watch the recording for the discussion of the first half of Module 11. Tuesday night or Wednesday afternoon. So alinman doon sa dalawa. Para pagbalik natin sa Thursday, start na tayo ng second half ng numerical or Monte Carlo simulation. All right? So I think that's it. Then just wait for the guidelines for the project next week. Ibibigay ko na siya para mapaghanda nyo na. Anyway, the final outputs will be due during the finals week. All right. Okay, so that's it for today. Thank you guys for joining me today. Enjoy your lunch, and then let's see each other again next week. Bye, everyone.
Thank you
Thank
po,
you po,
sir.
sir.
All right.